Introduction to Trigonometric Functions. SOHCAHTOA. This is an acronym that will help us remember the definition of trigonometric functions. Given a right triangle with angle theta as shown, we define the trigonometric functions for sine, cosine, and tangent as ratios of side lengths as follows. First, let's take a look at our right triangle. Here is my angle theta. The side that is closest to theta, that is not the longest side, is the adjacent side. The side directly across from theta is the opposite side. And the longest side, the side opposite the right angle, is called the hypotenuse. We define sine of the angle theta to be equal to the ratio of the opposite side length over the hypotenuse length. So sine is opposite over hypotenuse. That's S-O-H. That's the SO part in SOHCAHTOA. We define cosine of the angle theta to be equal to the ratio of the adjacent side length over the hypotenuse. So here we have cosine is equal to adjacent over hypotenuse, the ka part of SOHCAHTOA. And finally, we define tangent of theta to be the ratio of the opposite side to the adjacent side. So the side opposite the angle theta to the adjacent side of the angle theta. And that's the TOA, T-O-A. part of SOHCAHTOA. In this example, we're asked to find the sine, cosine, and tangent for angle theta. So here's theta inside of a right triangle, and we have the side length that is opposite of theta, so 6 is the opposite side. We have the adjacent side length given as 12, so this is my adjacent side length. But what I'm missing here is the hypotenuse, the longest side, the side opposite the 90-degree angle. Well, what we know about right triangles is that they follow the Pythagorean theorem. So we know that the two legs, which are the smaller sides of the right triangle, if I take each leg and I square it and I add it together, that's going to equal the length of the hypotenuse squared. So we might be used to seeing it as a squared plus b squared equals c squared, where, again, the legs are a and b. So let's go ahead and say that a is 6 here and b is 12. And we're interested in finding the length of the hypotenuse, c. So I'm going to go ahead and substitute in 6 and 12. So I know 6 squared, plus 12 squared is equal to c squared. And we have 36 now plus 144 is equal to c squared. And this is 180 is equal to c squared. Well, I want the value of c, so I have to take the square root of both sides. Now, when I take the square root of both sides, technically what comes out is plus or minus. So I have plus or minus the square root of 180 is equal to c. All right, well, since we're talking about a triangle here and side lengths, we can't have a negative length for the hypotenuse. So the value that we're looking for is just the positive value, so positive the square root of 180. However, we do want to simplify this further. We want to be able to simplify the square root of 180 because there is a perfect square that is one of the factors of 180. So we can see that 180 is divisible by the perfect square 9. It's also divisible by the perfect square 36. So we can either take this in steps or kind of do it all at once depending on what we see. So if we recognize that 180 is actually 36 times 5, then we can rewrite this as 6 radical 5 as the value of c that I'm looking for. If not, I would have had to take a little bit of a longer route. Just kind of switch colors here. I could have recognized that 180 is 9 times 20, and then that would have given me 3 radical 20, but then I have to break down 20 as 4 times 5, and so the square root of 4 is 2, 2 times 3 is 6, and that's where 6 radical 5 is coming from. So it just takes more steps if we don't recognize the biggest perfect square factor of 180. But if we do, this is what we get. We get 6 radical 5 as our hypotenuse. Alright, so now to find sine, cosine, and tangent for the angle theta, we have all of our side lengths, right? So I'm going to put this as the hypotenuse, I'll abbreviate it. So sine of theta is equal to, so here's my angle, the opposite side over the hypotenuse. So 6 over 6 rad 5. It's the ratio of side lengths. Now here, because this is all being multiplied and divided, I can go ahead and cancel the 6's. 6 over 6 is just 1, so I get 1 over the square root of 5. Now here, 1 over the square root of 5 can be rationalized. So we typically don't want to see a square root in the denominator, so I can multiply the top and bottom by the square root of 5. So we'd end up with the square root of 5 over just 5. So the 2 square roots cancel and give us just 5. We have a radical on the top, which is fine. We've eliminated the radical on the bottom. And then we go ahead and find cosine theta. So cosine is adjacent over hypotenuse, the ca part, right? So we have 12 over 6 radical 5. And here we can simplify. So 6 goes into 12 2 times. So we'll have a 2 on the top, square root of 5 on the bottom. We can again rationalize, multiply the top and bottom by radical 5. So we get 2 rad 5 over 5 as cosine of theta. And finally, we can find tangent of theta by doing opposite over adjacent. So TOA, opposite 6 over adjacent 12. So 6 over 12 can reduce down to 1 over 2. So here we've done it. We found sine, cosine, and tangent for an angle theta that's inside of a given right triangle. We just defined sine, cosine, and tangent for a given right triangle. But now we want to redefine the trigonometric or circular functions for the angle theta, where theta is going to be an angle in standard position. So we're going to let theta be an acute angle in standard position with x comma y, the point on the terminal side of that angle on the circle with radius r, so that x squared plus y squared equals r squared. So let's pause and take a look at the corresponding image. So we have this angle theta in standard position, so we're assuming it starts on the positive x-axis, and the terminal side, it intersects this circle, so we're assuming this circle continues on, we're just looking at quadrant 1. So we have that the terminal side intersects this circle of radius r at this generic point here that we're calling xy. And so by definition, the equation of a circle is x squared plus y squared equals the radius squared, and we've called the radius r. We are going to define sine, cosine, and tangent along with their reciprocals, cosecant, secant, and cotangent as follows. So now we're going to go ahead and define sine theta as y over r. So the y value of the coordinate point over the radius. And we're going to define cosine theta as x over r. So we have the x value of the coordinate point over the radius. And tangent theta is going to be the y value over the x value, as long as the x value is not 0, because we can't divide by 0. We are also going to introduce and define the reciprocals of sine, cosine, and tangent. So the reciprocal of sine is cosecant. So we have cosecant theta is r over y. So reciprocal as in the numerator and denominator switch. The reciprocal of cosine is secant. So secant theta is r over x. And the reciprocal of tangent is cotangent theta. So the reciprocal is x over y, but y cannot equal 0. And here, again, we cannot have the denominators equal 0. Notice in the first two, we don't have the stipulation that r cannot be 0, because it's not possible that r be 0. R is the radius of a circle, so we wouldn't have a circle if the radius was 0. In this example, we want to find all 6 trigonometric functions for theta if the terminal side of the angle passes through the point 5, 12. So here we've been given the x and the y value, a coordinate point. All we're missing is the value of r. So as a reminder, we just said that sine of theta was equal to y over r. Well, that radius can be found using the equation of the circle x squared plus y squared equals r squared. So we're going to go ahead and substitute in 5 squared plus 12 squared is equal to r squared. So we get 25 plus 144 is equal to r squared. So 169 is equal to r squared. When I take the square root of both sides, I will get plus or minus, and the square root of 169 is a perfect square. We get 13. So 169 is a perfect square. Its square root is 13. So we have r is plus or minus 13, but in the context of the problem, r is the radius of a circle, so r can't be negative. So our value of r is positive 13. Now, sine of theta, again, is y over r, so we're going to have 12 over 13. Cosine of theta is x over r, so we're going to have 5 over 13. Tangent theta is y over x, so we have 12 over 5. And we introduced our reciprocal functions as cosecant, secant, and cotangent, and cosecant is the reciprocal of sine, so we're just going to switch the numerator and denominator. We get 13 over 12. For secant theta, the reciprocal of cosine theta was going to be 13 over 5. And the reciprocal of tangent theta is 5 over 12, which gives us our cotangent theta value. Now, we solved the problem, but to go ahead and connect back, what we're going to do is take a second to sketch what we just did. So we're told that we have an angle theta and the terminal side passes through 5, 12. So I'm going to go ahead and sketch just a little quadrant 1 here. And so we have, I'm going to say this right here is 5, and this is 12. So the terminal side of an angle passes through that coordinate point up there. Let's see here. So we have up here at 5, 12. So that's the coordinate point that the terminal side of the angle passes through. So here's my angle, here's my theta. And this point, what we're saying is it's part of a circle, and we found that the radius of that circle was 13. So here, I'm going to go ahead and attempt to draw a circle here. I'll just make it like a dotted circle. It's not perfect, but we're going to go ahead and pretend here that this point, 5, 12, passes through a circle, and what we know about that circle, because we solved, is that its radius is 13. So here, that's this length from the center of the circle, from the origin to that point, is a length of 13. Well, what we can do is we can add just one line here to make this familiar and connect some ideas. I can go ahead and drop a perpendicular line. I can go straight from that point down to the x-axis, and if I go straight down, that's going to create for me a right triangle. So we had an acute angle, my angle theta, we had a point on its terminal side, an x and a y. That allowed me to find the radius r, which is the radius of a circle that point falls along. But if I go straight down from the coordinate point to the x-axis, I can form myself a right triangle. And let's see what we know about this right triangle is we know its hypotenuse length is 13, that's the radius, and I know its side lengths. So this length here is going to be length 5. How do I know? Well, how do I get to the coordinate point 5, 12? I'd have to go to the right 5, so this is 5, and this height here has got to be 12. So this is 5, and this right here is 12. And we have our adjacent side, our opposite side, to our right triangle. So sine theta is not only y over r, in terms of the coordinate point, the y value over the radius, it is, in terms of this right triangle, opposite over hypotenuse. So we really just redefined the 6 trigonometric functions, but at this time thinking about the angle theta being an angle in standard position with a point given on the terminal side of the angle. So to summarize what we just said, we want to note that for a non-quadrantal angle theta, so here's my theta, a right triangle can be formed, and we can see that x squared plus y squared equals r squared, which was the equation of a circle. It represents the Pythagorean theorem. So we have this base is x, this height is y, this radius here r, really just becomes the Pythagorean theorem. The two legs of the right triangle, each squared and added together, gives us the hypotenuse squared. However, we're going to see that this equation, it still holds true for quadrantal angles, as we'll see in the next example. So for non-quadrantal angles, we saw that it worked. Remember, that means not on an axis. So any of these interior angles, we can draw ourselves a triangle. But what we're saying is that this equation is still going to hold true even when we have a quadrantal angle, which we'll take a look at. And one of the things I want to just go ahead and mention is, since we are dealing with right triangles and the Pythagorean theorem, these are some common Pythagorean triples that are worth memorizing, so we don't constantly have to use the Pythagorean theorem unnecessarily. So 3, 4, 5, 6, 8, 10, 9, 12, 15, 5, 12, 13, which is the one we just solved for, 7, 24, 25, and 8, 15, 17 are all common Pythagorean triples. In this example, we want to find all 6 trigonometric functions for theta if the terminal side of the angle passes through the point 0, 3. So again, we have our x and our y value. So we can go ahead and solve for r using x squared plus y squared equals r squared. So we have 0 squared plus 3 squared is equal to r squared, or 9 is equal to r squared. So we get plus or minus 3, since 9 is a perfect square. And again, the radius has to be positive, so r is equal to 3. So now, if we want to go ahead and find all 6 trigonometric functions, we know that sine theta is y over r, so we get 3 over 3, which is just 1. Cosine theta is x over r, so that's 0 over 3, and 0 over 3 is equal to 0. Tangent theta is y over x, so we have 3 over 0, but we can't divide by 0, that's undefined, so we'd say tangent theta is undefined. Now we can go ahead and move on to the reciprocals. Cosecant theta is the reciprocal of sine. Well, we had 3 over 3, which was just 1, so if I switch those, I still end up with just 1. the reciprocal of secant theta is cosine. Now, we had 0 over 3, which simplified to just 0. But if we switch the numerator and denominator, we're going to get 3 over 0, and that's undefined. And then here, so we had originally 3 over 0, which gave us undefined. So now if we switch the numerator and denominator, we get 0 over 3, which is 0. So here we have found all 6 trigonometric functions, given that we passed through the point 0, 3. But let's go ahead and do a quick sketch of what's happening here. So I have an angle theta that's in standard position. It starts on the positive x-axis, and the terminal side passes through the point 0, 3. Well, that's up here. This is my coordinate point 0, 3. It's up on the y-axis. It's a quadrantal angle. And in fact, it's a very specific angle. It's 90 degrees. So this is the terminal side, right, of my angle. And here, I actually cannot form a triangle. So if this is my angle theta, I can't form a triangle here using this angle theta as one of my interior angles. So sometimes what students think is, oh yeah, I can form a triangle. I can do this right here. So we actually cannot form a triangle that has this shape over here, because then you're assuming that like this angle right here or this angle right here is the angle that we're talking about, but it's down here. So I cannot form that triangle. So there is no right triangle that can be formed when my terminal side passes through a quadrantal angle. So this angle theta is actually 90 degrees. But we can use this alternate definition of the trigonometric functions, this idea of y over r and x over r and y over x, to obtain the values. We didn't need to construct a right triangle and use opposite over hypotenuse, etc. So that's what that last note mentioned, that we can still use that definition in order to evaluate the quadrantal angles for all 6 trig functions. So now a quick note. So note that if we chose any point along the positive y-axis on that previous example, we would have the same values for all 6 trigonometric functions. That is because the trig functions are dependent upon the input angle, which in the example above is 90 degrees or pi over 2. So I just dragged that picture here for a second that I just drew. So we said that that angle theta happened to be 90 degrees because the point that was given on the terminal side, that point that was given was 0, 3. But I could have been given any point along the positive y-axis and still have gotten the same values for all 6 trig functions, the 1, 0, undefined, 1, undefined, 0. It doesn't matter what point that I was given. So I could have been given 0, 2, or I could have been given 0, 1, which is really the nicest number, right? It's like the nice smallest number. But it doesn't matter what point I chose, because when I went to go solve for r, the radius is always going to be that y value. So if I chose the point 0, 2, the radius would be 2. If I chose the point way up here, 0, 100, the radius would still be 100. So I'd get 100 over 100 for sine of 90 degrees, which would still be 1. So the previous problem really could have asked us instead to, quote, find all 6 trigonometric functions for the angle 90 degrees. And we would write the answers as follows. So it's just kind of different wording here, but the idea is to understand that on the terminal side of the angle, I can really choose any point I want because the angle is the focus, right? It's dependent upon the angle that we've chosen. So in fact, finding all 6 trig functions for quadrantal angles, so any quadrantal angle, is actually a really simple problem, because we can always treat the radius of the circle as 1. So we can always focus on whoops, didn't mean to scribble it out. We can always focus on the nice coordinate point, quote unquote, right? The nice point along each axis. So here, like the nicest coordinate point to work with would be 0, 1. And the nicest coordinate point to work with, let's say, along the negative x-axis would be -1, 0. And down here, it'd be 0, -1. And over here, it'd be 1, 0. So since we can pick any point we want along the terminal side, why not choose just the nice point where the radius is going to be 1? Let's go ahead and take a look at an example that will reiterate what we just said. So find all 6 trigonometric functions for pi. So sine of the angle pi, well, is going to be y over r, right? This value by definition is going to be y over r. But we're talking about a quadrantal angle here. Pi is on the negative x-axis side. So what we can do is we can think about the point on the negative x-axis, -1, 0, and we want to pick that point in particular because it's going to give us a nice r value. So sine of pi is y over r. Well, if I choose the coordinate point on the terminal side, -1, 0, then r is equal to 1. So I can essentially ignore it, because now sine of pi is the y value 0 over 1, right? 0 over 1 is just 0. So I didn't even have to bother with 0 over 1. I could have just put the y value. I could have just put 0. So now let's look at cosine pi. Well, cosine of pi, cosine is defined as x over r, but again, I can just ignore r because r is just equal to 1. And so it's just the x value. So cosine of pi is just -1. And tangent of pi, well, the definition of tangent was y over x. So here we do have 0 over -1, which is just 0. And then we can do its reciprocals. So cosecant, well, here we'd be dividing by 0. So we have undefined for cosecant pi. For cosine of pi, the reciprocal secant pi would be still just -1. And then for cotangent pi, if I take the reciprocal of tangent pi, I'm going to end up with undefined. So the values at the quadrantal angles are just combinations of 0, 1, -1, and undefined. So here's a table of the function values of the quadrantal angles. So on this left-hand side, this table has the quadrantal angles 0, 90 degrees or pi over 2, 180 degrees, which is pi, 270 degrees, which is 3 pi over 2. And it has across the top all of the trig functions, so sine, cosine, tangent, cosecant, secant, cotangent of those angles. So sine of 0 is 0, and sine of 90 degrees, or sine of pi over 2, is 1. Sine of 180 degrees, or sine of pi, is 0. And then sine of 270 degrees, or 3 pi over 2, is going to give us -1. So we can just see by quickly looking across this table, as I mentioned, all the values of the quadrantal angles are going to be 1, -1, 0, or undefined. So now, what if we want to evaluate the 6 trig functions given non-quadrantal angles? We're going to start by reminding ourselves about some special right triangles. Special right triangles. The following are 30, 60, 90 and 45, 45, 90 special right triangles with side ratios given. Here I have a 30-degree angle, and opposite it has a side length of 1. My 60-degree angle has an opposite side length of radical 3, and opposite the 90-degree angle is a side length of 2. The length of the hypotenuse is 2. So down here I can see my 30, 60, 90 angles correspond to side lengths of 1, radical 3, and 2 for this particular 30, 60, 90 triangle. But I can take this triangle with the same angles and scale it up or down. So I can shrink it down or I can expand it, but the ratios of the side lengths will still hold. And the ratios will follow this 1x, radical 3x, 2x that we have down here. So we're just going to double everything, or maybe we'll shrink everything and divide everything by 2. But the angles will still hold. Here I have a 45, 45, 90 right triangle, so it's isosceles. I have two angles that are the same, and opposite those 45-degree angles are side length of 1 in this triangle. Opposite the right angle is a length of radical 2. The hypotenuse is a length of radical 2. So in a 45, 45, 90-degree right triangle, the side lengths here follow 1, 1, radical 2. And I can also shrink it down or expand this 45, 45, 90, and the side lengths will still follow this ratio here. So 1x, 1x, radical 2x for the two legs and the hypotenuse. And finally here, I have the exact same 30, 60, 90 right triangle. It's just the emphasis is now on the 60-degree angle because it's in the bottom left-hand corner, but its ratio is still the same. So opposite 30 degrees is still 1, opposite 60 degrees is still radical 3, with a hypotenuse length of 2. In this example, we want to find the 6 trigonometric functions for an angle measuring 60 degrees. So now we're able to evaluate more trig functions with specific angles besides the quadrantal angle. So now we are adding 30, 60, and 45 degrees. So sine of 60 degrees can be found using this special right triangle where 60 degrees, I'm thinking about it in this bottom left-hand corner, and opposite 60 degrees is going to be a side length of radical 3, and the hypotenuse is 2. So opposite over hypotenuse, radical 3 over 2 is my answer. To find cosine of 60 degrees, well, cosine is adjacent over hypotenuse. The adjacent side to 60 degrees is 1. The hypotenuse is 2. So I have cosine of 60 degrees is 1/2. And tangent of 60, tangent is opposite over adjacent. So we have opposite of radical 3 over adjacent 1. So radical 3 over 1, that's just radical 3. And then now, to find cosecant, secant, and cotangent, we can simply take the reciprocals of these values we just found on the left. So we have radical 3 over 2. So that's going to give me 2 over radical 3. We've just created a radical on the bottom situation, so we want to multiply the top and bottom by rad 3 to rationalize. We get 2 rad 3 over 3. Here, if we take 1/2 and find its reciprocal, we simply get 2 over 1, which is 2. And then here, we have radical 3, or radical 3 over 1. That's going to give us 1 over rad 3 as its reciprocal. Rationalizing again, it's going to give us rad 3 over 3. In this example, we're asked to give the exact value of each expression. Or we could have been asked to evaluate or simplify. So all of these are a set of instructions that are equivalent. So sometimes students kind of struggle with, I'm not sure what to do here because the instructions are slightly different. So we could be asked to give the exact value, evaluate, or simplify. And in all of these cases, we're trying to find the ratio of those side lengths, right? So sine of 30 degrees plus cosine of 270 degrees. We have to go ahead and find each one separately. So sine of 30 degrees. Well, 30 degrees has a special right triangle. So that special right triangle, I'm going to just go ahead and quickly sketch it. So I'm going to sketch my 30 degrees. Opposite 30 degrees was 1. And then opposite 60 degrees was square root of 3. The hypotenuse was 2. So sine is opposite over hypotenuse. So sine of 30 degrees is 1/2. So far, we have evaluated the first part. And now I have to find cosine of 270 degrees. Well, 270 degrees is one of our quadrantal angles, and it's the one that goes straight down on the y-axis. So I'm going to go ahead and sketch just the bottom part of the xy plane. Here we have 270 degrees, and I'm going to go ahead and remember that I can think about really any point I want on my quadrantal angles on that particular axis, and the easiest thing to do is think about the point that's a unit away, just a single unit away. So here it's going to be 0, -1, so that radius is 1. And I can simply say, well, cosine, that's the x value, right? It's x over r, but since the radius is 1, we can simply take the x value is 0. So we have 1/2 plus 0, and then now these are just numbers that we can add together, which is simply 1/2. Let's go ahead and try another example. Here we're being asked to evaluate or simplify cosine of pi over 4 minus tangent of pi over 4. Again, we have to address each one separately. And for both of them, the inside angle is pi over 4. Here our angle is in radians, but we should remember that pi over 4 is 45 degrees. So pi, remember, is 180, so 180 divided by 4 is 45. So we do have that special right triangle that we can use to evaluate here. So I'm going to go ahead and draw a quick right triangle. It's a 45, 45, 90. And we said here that the two legs are of length 1, and the hypotenuse is a length of radical 2. For cosine of pi over 4, remember that we are doing adjacent over hypotenuse. So we have 1 over the square root of 2. So we're focusing on this angle, doing adjacent over hypotenuse. But tangent, we're still using the same triangle because the angle is pi over 4, or 45 degrees, right? So this is the same thing, pi over 4. Tangent is opposite over adjacent. So we have minus 1 over 1, so just minus 1. So now here, we do want to clean this up a little bit. We have something here that has a square root on the bottom, so we want to rationalize it. If I multiply the top and bottom here by the square root of 2, I get square root of 2 over 2, again, minus 1. And here, I can combine these if I rewrite 1 with a common denominator of 2. So essentially, I'm like multiplying the top and bottom here by 2. 2 over 2 is the same as 1. And now since they have the same denominator 2, I can subtract across the numerator, which is just going to leave me with the square root of 2 minus 2 all over 2. So here, this would be my simplified answer I combined by forming those common denominators after I rationalized. Now let's move on to part C. Here we're asked to evaluate, again, or simplify tangent squared of 60 degrees plus sine of 180 degrees. Again, we have to do each one separate, and this is a little bit new. So tangent squared of 60 degrees, there's a note down here at the bottom. So tangent squared x is equivalent to tangent x times tangent x. Or another way to write it would be tangent x, all in parentheses, squared. So we can essentially write that exponent right after the tan part, before the input. But that's different than tangent of x squared. So we really want to be careful where the exponent goes, because tangent of x squared in those parentheses would mean tangent of x times x. So we just want to be careful about what exactly we're working with. So here, this is tangent 60 degrees as a quantity squared. So this is what we're evaluating here. Tangent of 60 degrees, we'll find that number and then we'll square it, right? And separately, we'll find sine of 180 degrees. So tangent of 60 degrees, that's one of our special right triangles. I'm going to go ahead and sketch a 60 degree right triangle here. So here's 60 degrees, opposite 60 is square root of 3. opposite the 30 degree would be 1, and then my hypotenuse would be 2. So finding tangent of 60 degrees is opposite over adjacent, so radical 3 over 1, or the square root of 3, and that quantity is going to be squared. And then our job is to find sine of 180 degrees. 180 degrees is a quadrantal angle. It is the left side of the x-axis. And again, we want to focus on the nicest coordinate point over here on the terminal side, which would be -1, 0, right, a distance of 1 unit away. And let's remind ourselves that sine corresponds to the y value. It's y over r. The r is 1, so the y value is simply 0. So here, we're going to add 0 on. And to simplify, the square root of 3 squared, the square root and the square cancel, and we end up with just 3. And in part D, I'm asked to evaluate tangent of pi over 6 minus 2 times sine of negative pi over 2. So we have radians again, and just a couple of new things here. So tangent of pi over 6, so that's going to be, one particular value. We'll evaluate that. And then here, we have this 2 on the outside. Well, 2 is just a number on the outside that's being multiplied by whatever the value here is of sine of negative pi over 2. So we don't distribute the 2 in. That's not a property of trigonometric functions. I can't ever take a value and pull it out of a trig function, and I can't take a number and put it into a trig function. So this 2 is just going to hang out on the outside and eventually get multiplied by whatever this value ends up being. The second thing is, there's a little note here, we use parentheses around the angle to be clear that we're evaluating a negative angle. So we don't always use parentheses around the angle. So notice here, tangent of pi over 6, the parentheses weren't used, although they could be. But here, we tend to just use parentheses to make it absolutely clear what is inside of the trig function. So in this case, it's a negative pi over 2. So let's start by working on tangent of pi over 6. Well, pi over 6 is a 30 degree angle. Pi is 180 degrees, so 180 divided by 6 is 30. So we'd be looking at a 30 degree angle. And opposite 30 is 1, opposite 60 is rad 3, the hypotenuse is 2. And tangent is going to be opposite over adjacent. So we're going to have 1 over the square root of 3. We'll hold off now on rationalizing, and we'll go ahead and work on this one. So here we have minus 2, so we're going to leave that minus 2 here, and we'll fill in this value. What is sine of negative pi over 2? Well, negative pi over 2, negative angles go in a clockwise direction, so we're going to go down pi over 2, and that's going to lead us to the same as 3 pi over 2, or 270 degrees, right? It's going to lead us straight down. And on a quadrantal angle, again, we focus on the coordinate point. That's a unit 1 away, so 0, -1 down here. And let's see, the sine value down here is the y value, so we're looking at -1. So sine of negative pi over 2 is the y value -1. So we go to the angle, which is negative pi over 2, and we read off the y value. So we have a -1 here. And so now let's go ahead and rationalize. So multiplying the top and bottom by rad 3, we get rad 3 over 3, and then plus 2. So I'm multiplying this -2 times -1, right? So these are multiplied together. The two negatives cancel, leaving me with a positive. To combine these, I need common denominators, so we'd multiply the top and bottom by a 3 here. And so we'll end up with the square root of 3 over 3 plus 6 over 3. And we'd have to leave that as radical 3 plus 6 over 3. Right? These are not like terms, they cannot be combined. So this is the best that we can do. Here's a table summarizing the function values of our special angles. So we have our 30 degrees, which is pi over 6, our 45 degrees, our pi over 4, our 60 degrees, which is pi over 3, and sine, cosine, and tangent of those angles. So we said sine of 30 degrees was 1/2, sine of 45 degrees was 1 over radical 2, which could be rationalized to be rad 2 over 2, and then sine of 60 degrees is radical 3 over 2, and we have our values for cosine, we have our values for tangent, and we know that cosecant, secant, and cotangent are the reciprocals for sine, cosine, and tangent, respectively. So we can just go ahead and flip the numerator and denominator. So for sine of 30 degrees, that was 1/2. Cosecant of 30 degrees is 2. For sine of 45 degrees, that was 1 over rad 2, or rad 2 over 2. And if we flip that, we get radical 2. Well, notice that the easier one to flip is going to be 1 over rad 2, because then you're just going to have a 1 in the denominator. But if we flip radical 2 over 2, we're going to have to rationalize it and make more work for ourselves. So there might be an easier version to take the reciprocal of to find our other function values over here. So this is a table of my special angle function values. I want to wrap up with some final reminders. First, remember that we are working with trigonometric functions, so they need an input variable. In other words, you never want to write just sin. You must write sine of x, or sine of theta, or sine of, and give a specific angle like 45 degrees. Second, here are the correct ways to read each trigonometric function. So we have sine of x, cosine of x, tangent of x, cosecant of x, secant of x, cotangent of x. So it may seem basic, but I've heard students in the past say x instead of cosecant x. So I want to just make sure that I'm making it clear how these are read aloud. I want to make sure that we know the difference between sine squared theta, which is sine theta times sine theta, versus sine of the quantity theta squared, which is sine times the quantity theta times theta, right? So making sure we know that the placement of the exponent matters. The next one, the use of parentheses around the input of a trigonometric function is to help determine the clarity of the input. So it's not typically used around a single positive angle, such as sine of pi over 3. We don't typically use parentheses here, but it can be. Parentheses would be used around a negative angle, such as cosine of negative pi over 3, and around a sum or a difference, such as sine of the quantity 30 degrees plus 60 degrees. When evaluating a trigonometric expression, be sure to rationalize your answer. Right? For example, don't leave your answer to sine of pi over 4 as 1 over radical 2, but rationalize to obtain radical 2 over 2. That's considered the most simplified version of the answer. When evaluating a trigonometric expression, do not simply convert the angle. This is one of the most common mistakes I see. So remember, the answer is a ratio of side lengths, right? So in other words, sine of pi over 4 is not 45 degrees. It's a very common mistake for students to just rewrite the angle in its alternate form, right, in degrees or radians, and not actually evaluate the trigonometric function. So sine of the angle is a ratio of side lengths. It itself cannot be an angle, right? It's a common mistake for students to convert the angle rather than find the trigonometric value.